My dear friends, today's our topic is the light emitting diode. So it is my request that please subscribe my channel. Okay. Now we're coming to the topic, the light emitting diode. Now this is a PN junction normal diode. Okay, this is P-type semiconductor. This is an N-type semiconductor. P having the majority carrier holes shown with the the white dots, and N-type having the majority carrier, they are the electrons shown by the black circles, black filled circles. Okay, when the diode is forward biased, when it is forward biased, how? Like P is made positive and N is made negative, then the electron and holes, they are moving fast across the junction and they are combining constantly. Okay, and what happened? Soon after the electrons are moving from N-type to the P-type silicon, it combines with the holes which are present here. Similarly, holes, they diffuse in the N-type and they neutralizes the electrons. With the result, when the electron and hole meets, then a pair disappear. Okay, when a pair of electron and hole disappear, what it results? It results the atom, stable atom. Okay, and hence it makes the complete atom more stable, and it gives the, then what happened? The atom gives the burst of energy in the form of the tiny packet of the photon of light. When electron and holes, they neutralizes, then the energy is emitted out. Okay, now here there's a red LED and there's a green LED. When here it is a positive potential and it is a negative here, then the red LED will give the light. But on the other hand, when here comes positive, here comes negative, this diode green becomes forward biased and the red becomes the reverse biased. Then the green LED will give the light. Okay. So this is what is the LET, light emitting diode. Here, like this is a N-type semiconductor, this is a P-type semiconductor, and in between there is an active region, and there are the two leads. One is at here, one is at here. Okay, and this is given. This is a negative terminal. The negative voltage will be applied here. This is a positive terminal. The positive voltage will be applied here, and there is a phosphorus layer on the above of the N-type semiconductor. Okay. Now what happens? Now there are electron and there are the holes. Okay, electron in the N-type and holes in the P-type. They start diffusing. They are now coming in the junction and they now mixed. They neutralizes each other. And neutralizing, what happened? Our semiconductor is such that when the electron and holes, they neutralizes, the blue photons, they are emitted out. Okay, when the blue photons, they are emitted out, what happened? Now when they just passes the phosphor layer, then yellow photons, then they are excited by the blue photons. When the yellow photons are excited, what's coming out through this type of the diode? Coming out the blue photons and the yellow photons. And when the blue and yellow mix together, they give the white light also. Because yellow is a combination of the, red and green. Okay, so when yellow mixed with, blue light, it gives the white light also. Okay, now this how this happened. Okay, here the light is coming, blue photons, yellow photons, and the white light. So this is a very good animation. Now you're looking here, this is a diode. The blue having the two terminals. One is shortened than the other to distinguish like which one is anode and which one is cathode. That's why now then this LED is used with the power supply, with the voltage, with the DC voltage through a resistor to limit the current. Okay, when this diode is connected with the voltage in a proper manner, like the anode with positive and the cathode with negative in forward biasing, then it is giving the light. It is giving light, just see. Now on the other hand, if you connect it in a reverse way, that its P type is connected to the negative supply, negative voltage, okay, then it does not give any light. It is off. It is on when proper forward biasing. Now look here, this is a P type, this is a N type semiconductor. P type is given a positive with respect to N. So this is a PN junction diode. Then the hole and electron, they are diffusing, they are neutralizing, and the photons are emitted out. And similarly, the same can be explained like that. There are the electrons in the conduction band, and there are the holes in the valence band. When the electron jumps from conduction band to the valence band, then they neutralizes each other, and the photon of light is emitted out. Okay. So it's giving light, forward biasing. Resistor is for limit the current. This is a resistor, Now there are two types of the LEDs, like the bicolor and the tricolor. The left hand side bicolor mean it gives two light, tricolor mean that one gives three lights. A red light, both are giving red light. Both are giving, the green light. Now only the third one is giving the yellow light. So third one is the tricolor, and the left one is the bicolor. Okay. So this is now that the bicolor LED. For the bicolor LED, looking here, if the positive is given at this point and negative is given at this point, then this diode becomes the forward biased. When this becomes the forward bias, then it will give the light, the green light, okay? And at that instant, the red will be off because positive is attached at the, this N type. So the positive potential, negative potential, green is forward bias, giving light. Okay, now it is a reverse that when positive is at the, positive is here, this is positive, this is negative. That means this diode is forward bias, it will give the light now. So which one is forward biasing? Now this is forward biasing. The green is at forward bias, it is giving light. Okay, the green is forward biasing. Now in case of the tricolor, this is the circuit diagram. Now this is a common cathode, right? Now what happens, how it gives the light now, let's see. Now when it is made positive with respect to this, okay, and no potential is given here. When this is positive, it will give the green light. So giving green light. When this is positive, then the tricolor gives the red light. Okay. Now when this is positive, both are forward bias, both will give the light, red light and green light, mixed together now, and mixing of the two light, red and green, that becomes here the yellow. Looking here, that becomes the yellow. There's a tricolor. So one to remember that this circuit is incomplete. It is left incomplete. It is upon you, to make it complete. That whether you want the red, you want the green, or you want the yellow. In that way, you apply the potential at here, and you complete the circuit. Now there are some semiconductor compounds. Okay, there are some semiconductor compounds, and they emit the light of the different colors, because pure silicon and pure germanium, it is not that which can give the all the colors. So exotic semiconductors are what? Materials use different p and n dopants. Dopants mean the addition of the imperative. We used to use a different type of the semiconductor compounds, like the gallium phosphide and silicon carbide and gallium indium nitride, like that. And it also depends the ratio of each, like the ratio gallium, the ratio of indium, the ratio of the nitride. Mean what the amount, how they are mixed, okay, and to form a semiconductor compound in what ratio, and the color depends upon that. So they are the different compounds looking. Okay, so it's very simple, but now we're coming here. What it is shown. There are the different compounds, semiconductor compounds. Now the wavelength which is emitted by a compound, and that the color, then the forward voltage which is required. For infrared, very less voltage, red 1.8, then like that, going along top to bottom, the forward voltage is increasing. What implies for blue color, if we want a blue color, somewhat more forward voltage is required as compared to the red color, because the red is having with less energy. Red is the longest wave. Okay, longest wave mean the formula E equals to h nu, hc over lambda. So the less energy is required. So okay, the forward voltage is increasing along going from top to bottom, and the different semiconductor compounds and the wavelength which is emitted out. Now here the graph is given, forward voltage versus the current in milliampere, and for infrared very less voltage, for red more voltage, for orange more voltage, and even for blue is still more voltage is required. So this is the formula for the energy gap and the wavelength which comes out. Now here, when the electron jumps from the conduction band to wavelength band, then the energy is emitted out in the form of the photons. Now the problem is what was the wavelength of the photons which comes out? It depends upon the energy gap from here to here. What's that the band gap is? Okay, what's this band gap? So Eg is the band gap between valence and conduction, equals to h nu. Nu is the frequency replaced with c over lambda. And we find the value of lambda from this expression. Okay, and lesser the energy gap, longer will be the wavelength. Okay, and if the Eg is more, then lambda will be short. They're inversely proportional. Fine. So this is a band gap. It depends upon the. Is this okay? Please subscribe my channel. Thank you very much.